Welcome again. My name is Michael Hicks. I'm your instructor in Business 602. What we're going to do today is take our next step towards modeling with data. And I have here a spreadsheet, and I have data for the United States in 2018. I have per capita personal income, the share of adults who have graduated from high school, the share who have graduated from college, uh, and then the share that have an advanced degree. So the second column of data here, the BA plus, includes the data from the third here. So many of you have asked, where are we going with this? So what we've done so far is we've done summary statistics. Summary statistics are part of the data analysis process that we would use to try to understand data in its most fundamental form. So, we want to know what's the distribution of data. What is the mean? What is the variance? What is the kurtosis? How is it skewed? What's this good for, right? Well, it's good perhaps just to know when we're looking at a set of data what it looks like. And almost every data analyst is going to begin with that prospect of let's examine what data looks like to try to learn something from it. The second thing that allows us to do, and this is mostly for business applications, are to compare things that we observe. So we're doing a business survey of in marketing. We're trying to get a sense of what people think about our products or how many people know about our products. We might randomly call several hundred households and we'll ask them, and that data will tell us something about familiarity with the product. Maybe we do that before and then after a marketing campaign to see if our marketing worked, or maybe we ask people about what they thought of a marketing campaign. And so when you get to marketing classes or management classes, you'll do more of these things. Perhaps we would want to use this process for quality control. And so for example, let's say we're comparing breakfast cereals and we have a machine that fills boxes of breakfast cereal. We know how much we think is in that box, and we would wish to know if the machine is actually operating as designed. If you're putting too much in or over a long period of time, that could significantly hurt your profitability. If you're putting in too little, it could hurt your bottom line. School kids now are doing scientific experiments this way all the time. You see them on, click on YouTube or the news where some couple of kids will compare the number of, and my favorite is chocolate chips in a chocolate chip cookie. So they'll melt down some chocolate chip cookies with water to reveal if they, what's the average and the variance of chocolate chips in each chocolate chip cookie in a container. Most importantly, for what we're doing, though, certainly as an economist or in finance, is to understand the sample distribution, and that will give us a way of making more important comparisons. And so, uh, simple characteristics are really what we've done for the last couple of weeks are basic tools. And some of you have done these, some of you have not. You're in this class because there's an expectation that you need a little bit more in this and economics to really move forward. So, but we do need more. And the most obvious thing we need is to be able to compare different means or to learn something about comparisons here. And the first thing we do in statistics is correlation. A correlation is a statistical comparison or two or more variables, usually describing the same population. Right, again, so correlation is a comparison of two and potentially more. We'll get to that later on in class. Variables describing the same population. And so we might want to know a same group of people or places or items. And so we might want to know, for example, if being left-handed is correlated with age, right? So um, there's a long-standing hypothesis that, or understanding that for a long time, left-handed individuals were taught to ignore that. My wife's family's got left-handed, a lot of lefties in it, and those lefties who are older I say great grandparent age were taught to work with their right hand, not their left hand, in the early part of the 20th century. And so you could look to see amongst people if left-handedness today is correlated with age, because now schools are indifferent to it. If you're a left, I have a daughter who's a lefty and two sons that are righties. Schools made no concern about who did what. They just let them flow with being either a lefty or a righty, and so it's possible we could correlate, whether or not you are self-reported as a lefty or righty based on your age. If you're over 80, maybe you were purged of that in school. If you're under about 60, you probably weren't. And so that would be an interesting hypothesis test. You can think of a million others out there. We might, in this data set that I have here for you, I may be interested in asking a question whether or not there's a relationship between the high school graduation rate, the number of adults who have at least graduated from high school, and the share of adults who have gone on to finish a bachelor's degree. Right, so that'd be interesting to know whether or not there's a correlation between the two. So does low levels of educational attainment in high school bleed over into college or vice versa? So we may want to do that. And the way to think about correlation is simply that it is the product of two expected values, right? What's the expected value of two variables, say x and y? Say high school is x and bachelor's degree plus is y, divided by the product of their variance, right? And you'll learn these formulas, but you'll never have to apply. I don't believe in most classes you'll have to apply those formulas, but it's essentially the correlation is a next step of a signal to noise ratio. So the product of the means, the expected value, which is the observed value minus some random error term, which we assume to be normally distributed, divided by the product of the variances. And so we can actually do that in our software here. So I'm going to do some data analysis just to show you. Well, I guess the first thing we want to do is just plot these to see if we see any observed variable here. So we'll insert a scatter plot at first, and let's select two sets of data, the high school and the bachelor's degree data, and see if they look like anything. And so to me as an economist, those are strikingly correlated. You may not see that yet. That there are variables here. There is a relationship between the y variable on the vertical axis, typically, and the x variable here on the horizontal axis. And so we would look at these and we'd say, gosh, the way we can determine correlation is that when there's low values of one, there tend to be low values of the other, right? And as the values of one go up, they're more likely to be associated with higher values of the other, right? And as the values get really high out here, they tend to get higher over here, right? So this is the folks who've been to college. Makes sense. Those are lower, or graduate from college, those are lower numbers, and these are higher numbers. So states that have a high share of people graduating from high school have, on average, a higher level of people who have graduated from high school. So let's just leave that there for now and see what else we can learn from that. Although, I say that, but there's a lot of variation, right? And if we were to draw a line comparing the two, we'll just add a linear trend line, right? And that's what it would look like if we were to draw the best fitted line. We'll come back to that because that's a more advanced method of observing correlation, right? So we're just going to do correlation to two variables. How much are they correlated? So we go to data analysis, right? And we're going to correlation. Right, so we're going to begin. I'm going to choose our input range here. I'm going to choose a high school and bachelor's degree, and I want to see if there's correlation. So these are 50 states in the Washington D.C. I want an output range up here where I can observe it close to the graph. There we go. All right, so what this first, I'm going to move this. What this tells us is, right, that in column 1 is correlated with itself 100% of the time, and column 2 is correlated with itself 100% of the time, right? That's the diagonal, and we can do more correlations. I'll show you that in a minute. And the diagonal is always going to be 1. So this is high school, this is BA plus, this is high school, and this is BA plus. Okay. And what this value, that's called the correlation coefficient, tells us is that there's a 40% shared variance between these two values. All right, so there's correlation there. And correlation exists between a 0 and a positive 1 and 0 and a negative 1. So an absolute value, the correlation coefficient is always going to be between 0 and 1. The challenge that we have is that this is of limited value. It doesn't tell us, certainly doesn't give us causality. To establish causality, you have to do really one of two things. You have to construct an experimental design that allows for a treatment and control group, either before or after the same event, or we compare these observations to some other level, right? Or we have to have some theory that we're rejecting, that we fail to reject. Those are the two causal elements, and the more that you can be like an experiment, the better, but that's obviously not always an opportunity. We don't, in this case, typically have states that are going to, decide not to educate people with high school diploma, see how many go on to get bachelor's degree to satisfy our experimental interest. We're going to have to create some other mechanism to deduce that. And it may not always be possible. Not every experiment which we would like to test is testable. So the next step we go to then is to say, well, let's look if there are other correlations here. So now we would like to make we'll just do select the data here for bachelor's degree and bachelor's degree plus. Go back to look at that, and wow, that's a far stronger correlation, it would appear, and that's not unlikely, given that this number is included in this number, right? So everybody who is here has also been here as well, and so this is a much stronger relationship, both because, and we'll get to this later on, there is less variance around that regression line, and because it's a stronger slope. And so let's look in our data analysis and see if we can do a correlation here that would somehow give us some information about this. Let's put it in a place where we can compare it with the other value. Okay. So in this case, we have column 1 is BA plus, column 2 is greater than BA, BA plus, and greater than a BA. Right? And again, that trace of this matrix, or this diagonal of the matrix, is 1, but you can see now that the variance between the two columns is explained by 93%. All right, I'm just going to go to, make it clear that that's a percentage value here, right? And the correlation between holding the share of adults holding a bachelor's degree or higher explains 90% of those who have more than a bachelor's degree. And that's not surprising. But the high school graduation rate, or the share of adults with a high school diploma, only explains 40% of the variation in the bachelor's degree or higher. So there's not a lot of correlation there. Now let's look at let's take all three of these together and see if going back through our data analysis, if we can make a broader comparison. So we can actually compare 3 different variables here, and the software makes this easy. We can calculate this by hand, but it requires doing an awful lot of arithmetic that we wouldn't want to do. So this would be high school, BA or higher, and then higher than a bachelor's degree, right? And then those three variables also appear in this correlation matrix, right? And we'll get down to explaining this, right? So this is the trace against all three, right? Their high school diploma makes sense. High school diploma explains high school diploma with perfect certainty. So there's, the variance between the two, the expected value is the same and the variance is the same. So it's going to be 1 bachelor's degree, 1 higher than bachelor's degree, 1. Here, the high school and bachelor's degree is correlated with one another at 41%. And by the way, we could just we could just do the same thing and stick that there, right? Because that value is the same as that value, high school, right? The bachelor's degree at a high school has even less explanatory value to us. It explains only 20% of the variation between the two. And so what this means in statistical terms is that they're only 1 in 5 of the, or the variance, 20% of the variance is explained one by the other. In practical terms, what it means is there's always a number of people who have more than a bachelor's degree, no matter where your state is. That's going to be your physicians, your lawyers, right? And at the county level, the correlation is even lower. There's a stock number of people with more than a bachelor's degree. And there's always a sort of minimum share of people with a bachelor's degree because you have to have that, for example, to be a school teacher in most states, right? And we want to stick this one here, this 93%, the BA plus correlation is the same. So this gives us some statistical insight into what we're attempting to do, right? What's the explanatory value? And let's go back and just compare these again. We'll create a new graphic. Select data, right? And we'll just take a look at that compared to this is the correlation of the BA right. So in this case, really the correlation coefficient tells us how much. Here there's very little variation, not explained by this. There's very little variation from the expected line here, and here there's a lot of variation from it, right? And when we go off to a third chart, we see in this case even less correlation. So let's select the data of high school and BA plus, and then we have even more variation in that data. And that's really what that correlation tells us, is both the degree of variation and the stronger the slope. So the more, and I'll show you this in regression in a minute, because this is not the technique that most researchers deploy to understand a problem, but it's an insight of what we're trying to understand. All right, so what we're really trying to understand in any sort of example like this would be, what is the important relationship that we're comparing here, and is there a way to deduce some causality here that would be useful? And to do that, I'm just going to move to another worksheet and do a little bit of thinking about the problem here. So what we might suppose, given this data, is we might suppose that we would be interested in understanding the relationship between personal income and education. And we know clearly that there's going to be correlation here, right? It doesn't take a lot of rocket science to do this. What we really cared about here is the variation in what we anticipate and the strength of the relationship. And to do that, we have to move beyond simple univariate analysis that we did over the past 3 weeks. And we have to go beyond simple correlation coefficients, right? Because the relationship assumed in the previous example was all linear. It may not be a linear relationship. And what we really are interested in is beginning to work on theory. All right, so it's very easy to build a theory that there is a relationship between educational attainment and income, and that it's simply we can argue that educational attainment does one of two things. It either improves individual productivity, which would boost earnings, right? Or it signals the presence of higher ability. So even if you don't learn anything in high school, the fact that you've graduated from high school might signal that you're smarter and more productive. Same thing with a bachelor's degree or a master's or a PhD. And so what we really wish to do then, and we can sketch out a theory, there's plenty of theories on this, the human capital theory of growth, but let's just begin with some empirical work here. And we're going to start first by doing graphical examples we did before of a regression. We want to select the data. We want to see in this case whether or not per capita income, in this case we're looking at this, per capita income in a county is correlated with the share of people who graduate from high school. Well, that didn't work. Sorry, Excel's a little buggy, right? So we'll start off with that variable selected and that variable selected. We'll go to bachelor's degrees. We'll go to our insert, scatter plot, and there's our correlation. This is our basic regression, right? The problem is we have what we showed before. We have a trend line here, and that's really the relationship that we're modeling. And so let's see what we can learn directly from that. We want to format the trend line. In this data, we can display the equation on chart. So this equation is y equals mx plus b. So we're doing a linear model where y, which is the vertical axis, right, is a positive function, a small positive function, plus an intercept. That intercept is close to 0, right? And so we can actually visibly see that by backward, by running it through that variable, or through the back casting it, so we can see that that's the case, right? So that the problem is what we're doing here doesn't really by itself tell us everything that we might want to know, because we can oftentimes get some sort of correlation but isn't really strong enough for us to understand or to deduce anything from it. So in this case, I mean, 6e to the negative 6x is the slope here is not real big, and so what we would want to do is maybe do a bit of better analysis. So what we can do is regression, which is essentially a correlation coefficient that has with it two properties that we need. One is an intercept, right? So we're assuming a linear or some sort of quasi-linear function. And the second thing we're thinking about doing is trying to understand the how much signal-to-noise ratio there is between the observed variables in correlation. So if we were to have a lot of spread here, we may not be as confident that this is telling us a story. So let's erase this and look at a different one. We're going to select data now. We'll start with high school diplomas. and per capita income. This is the share of adults with a high school diploma in a state and per capita income. And you can see that's a flatter line, so there's less signal and there's more variation in the data, so it doesn't give us quite as much confidence as the earlier example. So without going any further, I'm going to erase this. We'll come back to these in a minute, and I'm going to show you the statistical technique that we want to do. So normally when you think about a linear regression, you're thinking about what you're doing is plotting a line in a linear model where y is equal to mx plus b. And so to do that, we'll go to data analysis. There's a regression function here alphabetically. And so what we can do is we want to input the y and x. So in this case, we want to see, and this is the opposite of what I illustrated just because there's a automatic y and x determination in the scatter plot here. What I want to do is pick our outcome measure as y. So our outcome is going to be per capita income. We're trying to see whether or not y, which is the left-hand side variable in our equation, y is equal to mx plus b, is correlated with let's look at high school diploma first. That's our x variable. So that's going to be our horizontal axis. The vertical axis is going to be per capita income. And here's our output. Now let's look about this first. The first thing we have is a coefficient value. We have an intercept, right? And this intercept is in dollars, right? Because it's the vertical axis of per capita income. The standard error is also in dollars. That's a pretty big standard error, right? So remember, the coefficient's effectively going to be this. That's our signal, right? And the standard error is the noise, right? So the t-stat is not exactly, it's a signal to noise ratio. So let's see if that signal divided by noise ratio looks anything like the t-stat. Well, looky there, right? The coefficients and standard error, this is that value, right? This is the probability that that value is higher than it would be in an accident, right? So what that really means is that 18 out of 100 times that that result could occur. So we don't think that that has any value, that intercept, right? Here is the signal to noise ratio, however, in dollars for this is the change in dollars, right? The x variable with respect to so y in this case is going to be equal to this, right, times x, right, which is an extra percent. I want that to be a text. No, sorry. This would be the mx, right, where that is the m and x is each one of these values, right? And this is plus b, and so y is going to be, mx is going to be that, right, times x, and b is going to be the intercept, right? And so this equation here gives us a slope of a regression line. Now let's just test that. T statistics is over 2. The value of that is lower than 1. So this result could only happen from a random draw of these variables fewer than 1 out of 100 times. So we have a lot of statistical confidence that this works. Remember back to my examples before when we talked about the statistical significance. We said there was typically a 1% level, which is met by that value. That's less than 0.01. There's a 0.05 level, which is commonly reported. That this would also meet the 0.05 level, and a zero point 0.1 level. This does not meet, this is higher than 0.1. So under traditional or generally accepted values, we would not have a lot of confidence in this. So economists, typically in graduate school, you would say this is not statistically significant, but this is. You might hedge your bets if this was really important, and let's say it was a 0.101. Well, that's going to be very close to a 0.099, which would be statistically significant. So you don't want to make too much of the threshold, but this is well outside the acceptable level here. So let's just see that t-statistic is really the signal to noise ratio, or the coefficient divided by the standard error. Look at that. That's the same as that value there, right? So what we were teaching before in signal to noise ratio appears here. So what we can say is that we're fairly confident in this regression, right, that we looked at. Does a bachelor's degree explain the level of per capita income in the county or in the state that we're looking at? So let's insert a graphic to visualize this as well, and I'll show you one of the problems with Excel and the process of doing that. So we're going to select data. We're going to pick high school. We're going to pick this variable on the vertical axis. We're going to pick this variable on the horizontal axis. And then we're going to add that trend line there, right? And you can see in this case that flipped the wrong way. Let me see if I can defeat one of the problems with software is that it has its interests without appealing to yours. So it doesn't matter what the variables to the left are always going to be y, and you have to just move them. So we're going to select data. We're going to have bachelor's degree. There we go. So the horizontal axis is the explanatory variable. In this case, it's going to be sorry. This is going to be per capita personal income. And this is going to be share of adults with a BA or, right? So this gives us a regression line. We'll add that trend line. A trend line is really a regression line, right? We're going to display the equation on chart and this extra little variable that I haven't talked about, right? And so there are a couple of things that are problematic about this. The regressions here don't tell us everything we would want. This is not the same x times b value there, right? 117,482, and that's 127,226, right? And that's the intercept 14,086, whereas the intercept here is 51,000, but really we could set it to 0. So let's see if we can make this serve our purposes. Format the trend line, set the intercept to equal to 0, and see how much closer that gets us, right? That gets us not a lot closer, but it is. We're assuming that we have no confidence that that intercept as it's drawn here, we're going to backcast it 150,000, is different from 0, right? So that's how we're going to draw that line. Well, I better back up. If we were to draw this line back down to 0 without it spoiling our axis values here and confusing us, would tell us something. So I never trust the Excel regression line here unless it's just illustrative, right? And in part because it doesn't give you statistical significance. The other thing that there are two other things that are of importance, and I'll go over them a little bit more formally in next week's class, that are important here, and that is that there is a two variables here, two signal to noise ratios that we haven't talked about before. The first one's an F statistic, right? And it measures the joint variance here, and it has a signal to noise ratio that is also subject to the same interpretation that the signal to noise ratio in the T statistics, which is simply that this value, if the p-value here is greater than 1 or is greater than 0.01, it's good to the 1% level. Or if it's less than 0.01 to the 1% level, if it's less than 0.05, it's at the 5% level, and 0.1 at the 10% level. And it turns out that in this case, in a single univariate value, the signal to noise ratio here is going to be identical to the statistical significance of the only statistically significant variable, or the slope. This is not. That goes away once you introduce multiple variables here. The other signal to noise ratio we have is the R squared. And the R squared tells us what share of the variance, the sum of all the variance of these from the regression line, or how much, essentially how far away they are on the average squared, is explained by that line, right? So the tighter the fit, the closer that will be. In this case, the multiple R squared is a 0.36, right? And the R squared is a 0.13. This is really, both of these are often reported. This is not often reported in software that is used by statisticians. The R squared is often reported by statisticians, but the most commonly reported value is the adjusted R squared, because this whenever you add variables together, the R squared goes up. So we can actually expand this analysis significantly by adding more variables to the right hand side. This value then drops as you add more variables, and it's a way to penalize a researcher for adding variables that do not explain additional variance, right? So the more you add, the more you see drop. So let me go over this again. This linear regression is the workhorse for most graduate program statistical analysis. It allows us to compare things that we would care about. An intercept, right? Is that statistically significant? And an intercept would be important because it would say what would be the value of per capita income if nobody graduated from a bachelor's degree. And so what these 51 observations say that there's no statistical agreement on what that might be. It's not statistically meaningful, right? The X variable here describes the relationship between per capita income and the share of adults who graduate from high school. So this has interpretation, right? Remember, the X is between 0 and 1. So if you went from, say, 50% to 150% of adults with a bachelor's degree or more, that would increase your per capita income by $117,000. So that's sort of ridiculous. Let's just see how much your per capita income would raise if you went from 50% to 60%. So you went equals point. It would be this coefficient. Sorry, equals this coefficient times 0.1. If you were a 10 percentage point increase um, in your sorry, I'm having memory problems. 0.1 times K24. So this is M is that value, X is the change, right? What would be the marginal change in per capita income? The answer is $11,000. So if you went from 24.5, let's just pick 24.5, and let's find one that's 25 point, close to 25.5. What will be the change in the expected change in your per capita income, right? We would expect there'd be $11,000 change. In this case, both Alabama's above the expected value, probably, and Indiana's below, but that difference measures the movement from like a point here to that to from 30% to 40%. How much was the vertical movement here, right? So that's that coefficient. Now, what's important to know about this is that this is the most basic of the workhorses that we would care about. And I'm displaying it here in a graphic because it's easy to see these things in two dimensions. We have here a X variable, the share of adults with a bachelor's degree or higher, and a Y variable, the per capita personal income. All right, and so those are very clear examples of what we might be interested in evaluating. And so in a very naive sense, we could take this result to a policymaker and say, how much richer in per capita income would an state be expected to be if they were to increase their share of adults who graduated high school or graduated from college? And the answer is, if you were to go by 10%, you were to go from 35 to 45 or 50 to 60%. The answer is that you would expect your per capita income to increase by $11,748. Now, the problem with this, which I think all of you can see, is that education alone, despite it being profoundly important, is clearly the most important thing that determines per capita income. It's not the only thing. What else matters would be you could think of a number of things that might matter. What are the industries that your state has? Some industries pay better than others, and for example, manufacturing pays high school graduates better than retail. So you would expect that if you lived in Indiana and you had a high share of uh, folks with a high school diploma, that they would make more money than Florida, that if they had an equal share of those with a high school degree only have more retail and tourism, which pays less well. The availability of physical capital or machinery would also explain some of the variance. The role of public capital. Do you have seaports and water and or river ports? Do you have railways and roads that can support commerce in your area? Do you have government that's effective in providing public services and safety? And so those are things that, maybe in the U.S. public services are fairly similar across states, but they're not. And you can see just the share of adults who've graduated from high school varies profoundly here in our sample, almost 10 percentage points. And so that would be a function of how good the public schools are in each of these states. And so in a research design, you would go from a single to a multiple regression type model. And I will show you that in the next class, in the next couple of classes. We're going to have to do some economics to make it seem like it makes sense. And the goal of that is to control for more variation in what we observe, right? So our research design goes from a simple correlation or one variable here. The more variables that we add change the coefficients on all other variables. So if we were to add industry mix here, or weather conditions, or share of manufacturing, or average age of the population, each of those would affect these variables in ways that are meaningful in explaining the relationship between each. So this raw correlation, or the regression between a share of adults with a bachelor's degree or higher and per capita personal income, tells us something interesting, but until we control for other variables, we wouldn't be really able to learn much about this. And frankly, all the theory that would tell us there's some causal inference here, or this correlation has some causal value, requires other variables in it, right? So we would care about the average age, we would care about the mix of industries and those sorts of things, as a theoretical explanation for why per capita income might be affected by education. And so what I'll do in later classes is show you that. Now, I'm not going to pop on screen. I just want to say it really quickly so that y'all hear. I don't give homework in this class. What I'll give next week is a worksheet of problems that you can solve. And the problems will be like what I've done in class. I want you to be able to operate software, to plot a scatter plot, to determine mean, median, standard deviation, the variance, the kurtosis and skewness of a sample. I want you to be able to compare sample means through a univariate t-statistic to see if they're the same. That's the result of your quality control. I want you to understand the central limit theorem from drawing a sample from a population. I'm then going to ask you to do simple correlation between two variables, and then I'm going to ask you to do regression with two variables, simple regression. And so those are going to be the tools that you have to have. And what I'm going to do in this class is ask you to find those variables from among those that I have illustrated in the very first class where I showed you where to get data. So I'm going to ask you to go out and get data on your own and do that, and then turn back into me the completed worksheet or spreadsheet that you have used to make those calculations. And that will be what the first test will be. So it's going to be a take-home test, right, that you're going to have several days to do this on, because I'm not going to give you an hour to test your download speed, to go download data and do the sorts of things that I want you to do. I want you to go on your own and find these things and develop a couple hypotheses on your own. So that's how I'm going to grade you, and that's really what's going to drive then what you walk out of this class with. So in a couple of weeks we'll be going into the economics component. You'll be seeing more of my good looking face as I show you the theoretical relationship between variables, which is really what economics is. Supply and demand, market analysis, consumer surplus, consumer welfare, the role of government, market failures, and then we'll go into macroeconomics. We'll talk about economic growth, we'll talk about inflation and the business cycle, and we'll talk about monetary policy and banking institutions. And that'll give you enough background, and in that process we'll be looking at some statistics that will give you information that you can then take into the next class. So I want this to be a class of doing, not just lecture watching, although what you've seen now are lecture watching. So what you can do is, I'm going to save this as a file that you can observe in the class, and it's going to be right. And so now you can observe in this class the material that I have, and you can download and do the same manipulation yourself. I will tell you these data come right from Wikipedia, the 2018 census data, which is a perfectly reasonable source. This data comes from the Bureau of Economic Analysis Regional Economic Information System. So if you're prepping for a class and you got to do it this weekend, go out and find your own data and do what we have done right here, and I think you'll be just fine in preparation. And with that, I'm going to stop recording and work on my next lecture for you. Have a good weekend.